Hi everyone, welcome to the session. Today we're going to be talking about the Amazon S3 Vectors feature. It's announced recently, it's currently in preview, but we're going to go through how to actually set up Amazon S3 Vectors, and we're going to show how to use Python to interact with the vector store. And I'm going to use both boto3, and I'm also going to use the langchain AWS SDK to interact with the data store. Now, before I start, I'm going to just give a little bit of an overview of what vector stores are. It's also shown in this blog post, but essentially what it is, it's a way of cataloging unstructured data. So this could be emails, PDFs, images, basically anything that doesn't have like a sort of CSV or sort of structure. So the way that it works is that you start with your unstructured data, you ingest it into the vector store, and to do that, you usually do some sort of AI operation to convert the text into a vector, and then you store the vector within the vector store. And then when you do a query, you take the query, you do the same process of converting it to a vector, and then you do a similarity to find the other vectors that are most similar to that one. So some of the use cases for using a vector store can be things like copyright detection. It can be similarity in images. It could be used as a very basic kind of similarity search within text. There's a lot of different use cases out there, and it's become quite popular with generative AI applications. I think the thing to bear in mind is because of the way that it works is it's actually just comparing vectors in the background. And so in some cases or some use cases, it might not be necessarily used as a very good search algorithm. But in this use case, I'm going to show you how to do like a very basic kind of vector search on the data. Yeah, so that's the basics. Let's start by heading over to the AWS console. So the first thing you want to do here is you want to go over and check which region you're in. At the time of recording, the S3 Vectors feature is only available in certain regions. For this demo, I'm going to use US East 1. I would recommend taking a look at the docs to make sure that you know exactly which regions the S3 Vector features is available, and so you don't get any errors when you're trying to implement it with your code. So we're going to choose North Virginia, and from here, we are going to go over to the S3 console. So using the top search, we go S3. And now from the left panel, we are going to go over to vector buckets. And here we are going to just create a vector bucket. We are going to give the vector bucket a name. So I'm going to just call it MAIB occurrences. And I'm going to append my account ID. You can choose an encryption type if you want to. For this demo, I'm just going to leave this out and not have encryption. And I'm going to click create bucket. Now you've got a very simple view. If you're watching this later, maybe a couple months from now, it's probably going to have a lot more details inside of it. But for this preview, you get the bucket itself. And if you open it up, you can just see a number of indexes. We haven't got one yet, so we're going to go over to create a vector index. From here, we're going to give a vector index name. So this is what we're going to be querying against when we do a query within our vector store. So I'm just going to call it the same MAIB occurrences. And the dimension is basically the size of the vectors. Now, the dimension that you use will very much depend on the machine learning model that you're using to create the vectors. In this example, we are going to be using the Titan models. There's a specific model that Amazon has for embeddings. You might be using a different one from OpenAI, or you might be using a different one from a different provider. It's important to have this number matching what the size is, because that's going to help to make sure that when you're doing the similarity searches that the operations are effective. So for specifically the Titan embeddings model, I know that it's got a 1024 dimension. When you're doing queries, it's going to be doing a similarity between the different vectors. And so here you can also choose which type of similarity you want to have. So for this demo, we're just going to keep it at cosine. And the last thing that you want to do is open up this additional settings. So under additional settings, we have the ability to create what is called non-filterable metadata. So first of all, the metadata is basically additional information that you can have with your document when you're ingesting it. So you might want to have things like the date, you might want to have like the original file, or you might want to have, who owns that file, or certain kind of metadata around it. Here you're specifying which fields are going to be available for filtering. By default, all of the fields are available for filtering, but if you have a particularly large metadata field, you might want to make it as non-filterable because there is a limitation in the size of a filterable field. So what we're going to do in our demo is we're going to actually have a metadata that's going to contain the actual contents of our file. And that is because when we want to query, we want to actually see the results of that query and the document that is returned. If you didn't have this, you would just get the result as basically an ID, and then you would have to then go and query the actual ID to get the contents of the vector. So for this demo, and to do this, we are just going to create a source text key. So we're going to create it as source text because in our metadata, we're going to have that extra field. Now we're going to just go to create vector index. With our vector index created and our vector bucket created, we're kind of complete within the S3 console. The last thing to do, and this is especially if you're new to AWS or new to the AI services, is we're going to go over to Bedrock over here. And here from the Bedrock console, we're going to go down and we're going to go to model access. What we're going to do here is we're actually going to enable the model that we're going to use to create that embedding. We're going to specifically use the Titan v2 embeddings model. And that is a specific language model that is going to take text and give out vectors. And so the way that you do this, I've already enabled it, but what you would do is you would go to modify model access. You might want to either select all of the Amazon models, but if you just want to follow this tutorial, just make sure you have Titan text embeddings v2. Just hit the checkbox and then you can go to next, and you'll basically have to wait a little bit of time, usually about like a minute or so, and then you refresh and you will have access to that model. So when you go back to model access, you'll see that. So now when you're back in model access, you can see that the Titan text embeddings v2 is shows access granted. If you don't do this and you try and do this tutorial, you will actually find out that you'll get an access denied because it will say that you don't have permission to access this model. So now that our model is enabled, we can head over to the code. Right, so for the code, I'm going to show you two ways of making use of the vector store. The first is we're going to use the AWS SDK, which is called boto3. This provides the sort of AWS way of accessing the vector store. And then I'm also going to show you how to use langchain, which is a very common library that's used to create LLM-based applications. And so you'll be able to see side by side how they work. I've got both of the pieces of code in a gist. It's in a link below. But the first thing that we're going to do is we're going to enable some environment variables. What I've done is if we look over at the first one in the Boto example, I use this package called .env, and this basically allows me to load in configuration from environment variables, and I can specify all of the environment variables in this .env file like this. This is just a kind of best practice that I'd recommend because it allows you to change the configuration without having to dig too much into the code, especially if you're building it for the first time. So a couple of the environment variables that we want to have is the region name. Bear in mind, this is because we want to make sure that we're using the vector store in the region that is enabled and also the region that we've just set it up in. We're going to use the Titan embed text v2 model. So here is the model ID. So for the S3 vector bucket name, I'm going to go back to our S3 console. I'm going to just select this bucket name here and I will paste it in here. And then the index name is this MAIB occurrences index. I've put here the an input data set. This is just going to be data that we're going to load into our vector store so that we have something that we can query against. I'll show you what that data set is. It's actually the MAIB is a data set of marine incidents. So you can see here there's a couple of It's basically got a, when an incident occurred. So if there was like a collision, or if, someone fell overboard, or if there was some sort of incident, it is recorded, and there's a description, there's like a date, which country is responsible for it, or basically which country it occurred in. And if you want to know more about it, you can head over. It's actually a downloadable data set from the UK government. So you can get this, occurrences table over here. So if you wanted to follow the exact example, you can do that. There's also some interesting data sets here. You can obviously, by all means, use your own data set. Just bear in mind that the scripts here have been created specifically for this data set. So you will have to do a few tweaks if you're using your own one. So the last environment variable here is max input documents. I've just got this because I want to only have like a small subset just for the tutorial purposes. Obviously, you would have to ingest the documents that you want to use for this vector use case. What I'm going to do now is go through a little bit of the code. So I'm just going to go through the example code to just show you a little bit of the inner workings of how it works. So we've got some common functions like this read CSV, and we've got basically creating two clients over here. The first thing to look at is this create vectors function. So what this takes in is it takes in a document, which is basically just each row of our data set. We're taking in a document. We're going to first of all create an embedding. The create embedding is going to invoke a Bedrock model. So that's that model ID that we set earlier. And then it's going to provide the text and get an embedding result. We're returning that. And then alongside the embedding, we're actually adding in our metadata over here. And we're also providing a key. So the key is a unique identifier for each of our documents. So bear in mind that the document could be an email, it could be an image, it could be a PDF. You're providing the ID as an identifier within the vector store. And then you're also providing metadata. Now, specifically for this use case and for this demo, I've also broken out the local date by year and month. And that's because I want to show you how to filter using the query filters. So the last thing to bear in mind for this function is that the description has been added as embedding, and it's also been added as the source text. So remember, we created that non-indexable filter. So this is the source text, and what we're doing here is we're essentially providing the description as metadata, so that when we do a query, you can just read the result. For your use case, you might not necessarily do that. You might just return the ID and then do a lookup of the actual document. But if it's small enough data, it might just make sense to just do it this way. And obviously for the demo here, we're just doing it so that we can actually get some feedback as to whether our query is working or not. We have this load documents function, which basically calls put vectors, which is another boto3 S3 vector function, which is going to take our vectors that we've created from this iterator, and it's going to put it into this put vectors, and it's going to put it into our vector store. There's a list vectors, which just does a list, similarly using the boto3 package. We've got query documents and query documents with filter. So for query document, you can see here how the query is performed. First of all, we take the query and we're going to create the same embedding. So that's going to take the query text, it's going to convert it into a vector, and we're going to get the vector back. And it's that we're going to use to query our vector data store. So you can see here, we're providing it here, and then this will return our response, which is our sort of top 3 most similar vectors. And that 3 comes from this top K. And top K is basically like just return the sort of 3 closest, or the K closest vectors to this one. So the next is query documents with filter. It's a very similar call. It still uses the query vectors. It's still creating an embedding. But here we can provide filters. And if you want to see the filter syntax, you can go over to the AWS docs to see that. Here for this example, I'm just using year and month. And what I'm just doing is checking for whether it's equal to year or equal to month. So that will allow me to filter for specific years and months, and then do the query on those on that subset. And then lastly, I've got just a small function to delete the vectors once I'm done. So I'm going to run this demo through the console, and the way I'm going to do that is using IPython. So I'm going to start with IPython -i, which stands for interactive, and I'm going to use the with boto .py file. So what that's going to do is drop me into an IPython shell so that I can play around with the functions inside of this file. So the first thing I'm going to do is the load documents function. And what that's going to do, as I mentioned, it's going to take a couple of lines from the dataset CSV. It's going to populate them into the vector store. So if I hit enter, it takes a little bit of time because what it's doing is for each of those documents, it's going to call Bedrock. Bedrock's going to respond with the vector, and then it's going to put it into the vector store. So it takes a little bit of time, usually between, I think, 10, 15, maybe 20 seconds. Obviously, the more vectors you have and the more documents you have, the longer it's going to take. So I'll just pause for a bit until that is loaded in. So our files are now loaded in. We can check that they're loaded by doing a list vectors function. And if we do list vectors, we can see that it returns a whole bunch of keys over here. So these keys represent the IDs of each of the documents. The next thing we're going to do is to query our index. And we're going to do that using the query documents function. So I've got query documents here, like this. And I've had a look at the data before, and there seems to be an issue with pilot ladders, and it's just seems to be a good query that tends to return some results. So I'm going to kind of search or do a vector similarity between our vector store and the words pilot ladder. And if I hit enter, you can see it's quite quick to query, and then we can see that we've got, mention of a pilot ladder. You get basically the source text, which we can see. As I mentioned before with the non-filterable metadata keys, is that if we were not to include this, you would not be able to see the actual text as you output it. So bear that in mind. Here you also get the distance. So the distance is the cosine distance between the two vectors. So the vector that we provided and this particular vector. And you can see it's ranked from smallest to largest. And it's only showing 3 because our top K is set to 3. If you set that to 1, it would just show the sort of closest similarity. The other function that I have is query documents. With filter. And what I've got here is that I can actually provide the dates. So I'm going to just go 2028. So I'm going to see all the incidents from August of 2024. And if I hit enter, you can see that it responds now with only items that have local dates set here. So you can see 08, 08, 08. And then again, it's showing the most similar, so the shortest distance. And you can see here it's talking about a pilot ladder, and you can see what happened with that incident. So that's the boto3 side. So the last thing I want to do before I move over to that is I just want to do, there's a delete vectors feature. And I'm just going to hit delete vectors. And then if I go list vectors again, you can see the list vectors shows 0 vectors. That's just because I want to now go over to the langchain side, and with the langchain side, I want to make sure that I'm populating it from scratch, as I did with this demo. So that's for boto3. Let's look at how you would do this with langchain. So for the langchain part, it's very similar. I've tried to replicate a lot of the functions from the boto3 example into the langchain example. So what you'll notice here is you don't have to import boto3 at all. That's because if you're using the langchain libraries, it's got a lot of that machinery built inside of it. I've got a lot of the environment variables set in a very similar way. The only differences here is that instead of creating the clients as I was doing over here, so you can see here you would create the clients, I'm instead creating these langchain objects over here. So there's one for Bedrock embeddings, which is going to allow our langchain application to fetch those embeddings. And we've also got the S3 vector store, which is a vector store object within langchain. And so it has a number of capabilities to store, retrieve, and delete vectors within that store. Again, we've got read from CSV. We've got a create document. Here, the create document, we're again using the description as the page content. And we're also breaking out the local date again. And we're also setting source text over here in our metadata. So you see, instead of creating the object like we were doing or creating the vector that we were doing in boto3, over here we're using the document object within the langchain libraries. And that basically represents a document with its metadata, its ID, and its contents that can then be ingested into the vector store. So that's the create document. Here we have load documents, where we're just taking this iterable and we're just adding the documents to the vector store using this add documents function. We've got, again, query documents. For this query, we're using similarity search with score. So this will basically do that distance search on the vector store. And then we also have a query documents with filter, and it's basically the exact same function. It's just adding this filters key where we're filtering on the year and the month. And then we've got delete vectors over here as well. So for the langchain example, we're going to use, again, IPython. I'm going to do -i, and then I'm going to go with langchain. We're going to drop into the IPython shell, and now we're going to do, again, we're going to do load documents. Again, here, what is happening is the langchain library is going to be calling the embeddings model in Bedrock. It's going to be returning vectors, and then it's going to be shoving those vectors into the vector store. And it takes a little bit of time, as I mentioned before. I'll pause until it is complete. Right, so our documents are loaded. It took about 15 seconds. The next thing we're going to do is to query the data store. As I mentioned, I haven't found a way to actually just list the vectors. I think it's very dependent on the type of vector store that you're using. So we'll leave out the listing part, but we will do the query documents. And then I'm going to, again, use pilot ladders as the query, and I'm going to just query it. And you can see it returns quite quickly, and you can see you've got similar pilot ladders. It's mentioning those words. Now, the thing just to bear in mind, at the time of this recording, there's no filter functionality built into the vector store similarity search library. I have got it in the code because I assume that it will be implemented at some point, but it might not just be available at this time. So if you wanted to do a filter search at this point, you can go and check that out using maybe boto3 if you want to. The last thing we want to do is delete the vectors. If we do that, we just get a very simple true, and in the background, the langchain will delete all of those objects. So that's it for the tutorial. The last thing I want to do is show you how to delete everything and clean everything up so that you don't incur any extra costs. If you head over back to the S3 console, you'll actually notice that some of the features like delete is not available. So the way that you get around this is you need to maybe use the CLI. Obviously, at the time of recording, it's not available, but by the time you watch this, it might actually just have a delete option. So what I'm going to do is I'm going to head over to the terminal. And I'm just going to use the AWS CLI. I'm going to go AWS. For me, I'm going to use a specific profile. You might not necessarily need to use a profile. I'm going to set the region as US East 1. And then it is S3 vectors, delete index, index name. And this is going to be our index name over here. So if I do that and then I go refresh, you can see that the index is gone. And the next one we're going to do is to delete vector bucket. And now if I go to refresh, I think you'll see, you go back to the vector buckets, you can see it's now deleted. And that's basically the end. So what we've covered is we've created the S3 vector bucket, we've created an index, and then we've used Python codes, both langchain and boto3, to ingest data into the vector store and also to query that vector store data. So hopefully you found this interesting and useful, and hopefully we'll see you next time on our next video. Cheers.